Welcome back to this channel on microeconomics. We continue learning about game theory. In previous videos, we introduced the basics of a game and found the easiest way to solve static games. That is the iterative deletion of dominant strategies. But the challenge was that this approach didn't find a solution in some games. So today we are going to explain one of the most well-known concepts in game theory, the Nash equilibrium, in order to find a solution in every static game. Today we are going to talk about Nash equilibrium in pure strategies, and in following videos we will introduce the mixed strategies to completely review the landscape of Nash equilibrium. As we have seen in previous videos, when the elimination of strictly dominated strategies doesn't help us find the solution to a game, either because there are no dominated strategies or because they are not enough to reach a solution, we need other ways to predict the outcome or solution of any strategic game. One possibility for predicting players' behavior, applicable whenever a game is static and with complete information, is Nash equilibrium. Nash equilibrium is a well-known concept which was named after John F. Nash, who formalized it in the 1950s during the last century. The life of this man was very well explained in a film called Beautiful Mind, started by Russell Crowe. Let us consider an arbitrary game in a strategic form. In what follows, we will denote the vector of strategies of the players in this game as in the screen, and we can define the Nash equilibrium as it follows. The vector of a strategy's profile is a Nash equilibrium if for every player I, the corresponding strategy S sub I is the best response to the strategies of the other players, called by S sub minus I. In other words, the utility or payoff that player I receives when playing this strategy profile, while the others play the same strategy profile, is always greater than or equal to the payoff received if player I were to play any other likely strategies, while the others continue to play the strategy introduced in this strategy profile. In an easier way, the Nash equilibrium is a vector of strategies such that if all players were to act according to it, and each knew this, no one would have any incentive to deviate. In most game theory analysis, it is usually assumed that players in any game will act according to one of its Nash equilibria. Since the justification for this hypothesis is complex, we will not study it in detail here. It should be noted, however, that its assumption is somewhat controversial, and its empirical validity remains a matter of debate nowadays. The notion of Nash equilibrium is weaker than the notion of dominant strategy equilibrium that we have seen in previous videos. That is, an equilibrium in dominant strategies is always also a Nash equilibrium. For example, the outcome cooperate in the prisoner's dilemma is also a Nash equilibrium. However, a Nash equilibrium does not necessarily imply the existence of dominant strategies. For instance, the Nash equilibria in the Battle of the Sexes or in the chicken game that we will see deeply in following videos are not equilibria in dominant strategies, as there are no dominated strategies in those games. Can this notion of Nash equilibrium be generalized? That is, it's true that a strictly dominated strategy can never be part of a Nash equilibrium. The answer is yes, regardless of the game considered. Moreover, it can be proven that if a strategy does not survive through the iterative elimination of dominated strategies, then it cannot form part of any Nash equilibrium. Let's see now how to calculate a Nash equilibrium using the following game in normal or matrix way. In general, if we have a payoff matrix like the one shown on the screen, we can find the equilibria by applying the following rule to all the cells of the matrix. This easy rule says the following. If the first payoff in a cell is the highest in its column and the second payoff is the highest in its row, then the corresponding strategy pair is a Nash equilibrium. Assuming, as defined in previous videos, that the first payoff in each cell corresponds to the row player. Let's start by finding the highest payoff for player 1 when player 2 plays the strategy L, that is the first column in the screen. We see that is 4 if player 1 chooses M, since 4 is greater than 0 and 3. Which are the other likely payoffs for player 1 when player 2 chooses L. Now we do the same for the second column when player 2 plays M, and find that the highest payoff for player 1 is 15 if they choose U. Finally, for the third column, when player 2 plays R, the highest payoff for player 1 is 1 if he chooses D. Next, we carry out a similar process for the rows. In the first row, when player 1 plays U, the highest payoff for the other player is 4 if they choose L. In the second row, the best response for player 2 is to choose M, earning 15. And finally, in the third row, when player 1 plays D, the best response for player 2 is to choose R, earning 8, the maximum payoff in that row. We observe that the only pair of strategies that serve as best responses in a simultaneous way for both players occurs when player 1 plays D and player 2 plays R, since both strategies are marked as best responses at the same time. Therefore, the only Nash equilibrium of this game will be D and R, and the players will earn 1 and 8 respectively. Let us now consider the game known as the Battle of the Sexes, which I have mentioned before. This game models a situation in which a couple must decide what to do together. Each person prefers a different activity, for example, beach versus mountain, football versus theater, cinema versus ballet, dinner with one's parents or the others, but both prefer doing something together rather than in a lonely way. The payoffs in this type of game can be represented in a matrix like the following one, where A and B stand for any of the two activities mentioned before. What is or are the Nash equilibria in this game? Let's solve it in the same way as the previous game. If player 2 chooses A in column 1, the best response for player 1 is to choose A because 9 is better than 0. If player 2 chooses B in column 2, the best response for player 1 is to choose B because 1 is greater than 0. Looking by rows, if player 1 plays A, the best response for player 2 is also A, since 1 is greater than 0. And finally, if player 1 plays B, the best response for player 2 is also B, since 9 is greater than 0. We can see, therefore, that both A and B are equilibria or solutions of this game. In other words, the couple will always choose to do the same activity, either A or B, but never separate ones. This is a multiple solution situation because in this case there is more than one Nash equilibrium, 2 in fact, and the payoffs of each equilibrium are symmetric. What one player earns in one equilibrium is what the other earns in the other, since the one whose preferred activity is chosen will earn a little bit more. What does theory predict when there are multiple equilibria? Well, sometimes the concept of a focal point, introduced by Schelling in the 1960s of the last century, is used to resolve this type of problem. See documentation and examples from the interactive class sessions for deeply explain this concept of the focal points. The problem that can arise with an equilibrium in pure strategies, as we have seen in this video, is that sometimes it does not exist. Let's illustrate this issue with the game rock, paper, and scissors, whose payoff matrix is as follows. If one player chooses rock, the best response for the opponent is to play paper. If one player chooses paper, the best response for the opponent is to play scissors. And finally, if one plays scissors, the best response for the others is to play rock. Therefore, there is no pair of strategies that are best responses for both players in a simultaneous way. In other words, the rule we have been using to find Nash equilibria in pure strategies yields no result in this game. Why? Because there isn't one. A Nash equilibrium in pure strategies doesn't always exist, as we have seen in the case of rock, paper, scissors, or for example, in the game heads or tails. To solve this problem, theorists developed the concept of mixed strategies, which we will explore in the following video.